Hi everyone, my name is Kiana and today we'll be going over acid and base equilibria. Specifically, we will be reviewing that what an acid and a base is, how the acid ionization constant relates to equilibrium, as well as a real-life example. Before we dive into how the acid ionization constant and pK value relate to equilibrium, we have to get down to the basics. An acid can be defined in two ways. According to the Bronston-Lowry definition, which is all about proton exchange, an acid is a proton donor. According to Arrhenius, an acid is a substance that, when dissolved in water, increases the concentration of hydrogen ions. An example of an acid is sulfuric acid. A base can also be defined in two ways. According to the Bronston-Lowry, a base is a proton acceptor. According to Arrhenius, a base is a substance that, when dissolved in water, increases the concentration of hydroxide ions. An example of a base is potassium hydroxide. This image here relates to the Bronston-Lowry theory on acids and bases. This is a crucial image to understand in order for you to understand the further concepts being taught. As you can see here, the proton from this molecule is being donated to this molecule here. That makes this molecule the acid and the acceptor the base. A conjugate acid contains one more hydrogen ion and one more positive charge than the base that formed it. A conjugate base contains one less hydrogen atom and one more negative charge than the acid that formed it. In an acid-base reaction, the equilibrium will favor the reaction that moves the proton to the stronger base. A strong acid is defined such that when it dissolves in water, like hydrogen chloride, it ionizes completely. This means that every molecule of acid will transfer to the acidic proton to a water molecule. If every molecule reacts to completion, this will make things neat and tidy. On the other hand, weak acids are defined such that when dissolved in water, such as hydrogen fluoride, only a fraction of the molecules ionize. An equilibrium is established between the ionized and the unionized form. This needs some math in order to determine final concentrations. The acid ionization constant is similar to Kc for generic equilibrium as learned in previous modules. Ka is a measure of how thoroughly an acid-base reaction proceeds in the forward direction. This value is determined by dividing the concentration of the products over the concentration of the reactants. Water is not included in this as it is a pure liquid. Any pure substance is not included in this equation. The value of the acid ionization constant can tell us a lot about a reaction. A larger Ka value, meaning that it is much greater than 1, means that there are more products and therefore a stronger acid. This indicates that the reaction is more acidic and will have a lower pH value. A smaller Ka value indicates that there are more reactants and therefore a weaker acid. An example of this is carboxylic acids, as they are known to be weak acids. Moving on to a core concept in acid-base equilibria, which is pKa. This is the negative logarithm of the acid dissociation concepts. Essentially, pKa tells you what the pH needs to be in order for a chemical species to donate or accept a proton. Now, you may be wondering why this number is used instead of the acid dissociation constant. Well, this is because the pKa describes acid dissociation using small decimal numbers. The same type of information may be obtained from Ka values, but they're typically extremely small numbers given in scientific notation that are hard for most people to understand. The lower the pKa value, the stronger the acid will be. The pKa value can be used in order to determine which way a reaction will proceed. Weak acids and bases are lower in energy than strong acids and bases, and because equilibria will favor the reaction side with the lowest energy species, acid-base reactions will go to the side with the weakest acids and bases. Let's look at this example right here, between this reaction of hydrogen cyanide and acetate as an example. Due to the fact that hydrogen cyanide with a pKa of 9 has a higher pKa than acetic acid, the equilibrium will lie to the left in the direction of the weaker acid and base. Before we dive into our example and real-life applications, it is crucial to understand the importance of water in our acid-base equilibria. All acid-base chemistry takes place in the presence of water. An infinite amount of water is surrounding every acid or base, so this can be ignored, as there's always going to be water. However, water's role is very important as it is amphoteric, which means that it can serve as an acid or a base. Looking at this example here, we can see that water accepts a hydrogen ion, having hydronium as a conjugate acid and thus acting as a base in this example. Over here, we can see water donating a hydrogen, having hydroxide as its conjugate base, and therefore, in this example, water was acting as an acid. Also, water has autoionization properties, which basically means that it can self-conduct. Let's look at this example. Here, we're asked to determine the Ka of phenyl if given 0.1 moles of the solution with a pH of 5.43. The first thing we need to do is write out our balanced chemical equation and write out an ice table. By using an ice table, we can determine the concentration values. I won't be going over the specifics of how to construct an ice table as this should be learned in the previous modules. The next step is to determine the concentration of hydronium, which can be deciphered by using the formula 10 to the power of the negative pH, and the pH value was of course given in the question. By plugging in the values, we get the hydronium concentration to be 3.7 times 10 to the negative 6 moles. Since this is the value of X in our concentration equation, this value will be used later on in order to determine the Ka. The last step is to plug everything into the Ka formula. We know that Ka is the concentration of the products over the concentration of the reactants. By plugging in the values, we get Ka to be 1.4 times 10 to the negative 10. By taking this a step further, since this Ka value is very, very small, we can determine that phenyl is a weak acid due to its very minuscule Ka value. Did you know that the pK of a drug is a crucial element in the pharmaceutical world? The acid-base dissociation constant, pKa, of a drug is a key physiochemical parameter influencing many biopharmaceutical characteristics. The pKa of a drug is the hydrogen ion concentration, otherwise known as pH, at which 50% of the drug exists in the ionized hydrophilic form, meaning an equilibrium with its unionized lyophilic form. All local anesthetic agents are weak bases. At physiological pH, the lower the pKa value, the greater the lysophility. For most local anesthetics, the pKa is in the range of 7.6 to 8.9. Thank you so much for listening to my presentation. I hope you learned something new, and here are my references. Have a great day!